So we have to do the same thing with the y momentum equation. So we've done the continuity equation, we've done the x momentum equation. Here's the y momentum equation, right? So we have y momentum terms, we have pressure force and then viscous forces. Again, we're going to take the order of magnitude of each of these terms one at a time. So let's start over here on the left. So the first term here, the order of magnitude is rho times u, so rho times u infinity, and then dv dx, so v delta over L. When we continue along, we have rho times v, so v delta, and then dv dy, so v delta over w. I'm sorry, v delta over delta. We'll leave the pressure gradient alone. We'll do the last two terms. So this is mu times the second derivative of v with respect to y. So as we talked about before, this is going to be the derivative of the derivative. So this is v delta over delta squared. And then mu times d squared v dx squared. So this will be mu times v delta over L squared. So every place we have a v delta, we can substitute in our scaling for that v velocity, that y velocity. So that's u infinity times delta over L. And you can see here what you get. So you get, for this first term, rho u infinity squared over L times delta over L. And the same thing for the second term, and actually the same thing for this term. And this term actually is rho u infinity squared over L times delta over L. And then you have a 1 over the Reynolds number. So this term, given that the Reynolds number is large relative to 1, this term is going to be much smaller than the others. So what we've learned here actually is that all of these terms that we've looked at are rho u infinity squared over L, that order of magnitude, times delta over L. So they're actually smaller, a lot smaller than rho u infinity squared over L. And if you remember, rho u infinity squared over L, that was the order of magnitude of all of the terms that we retained in the x momentum equation. And we've just looked at all of these terms in the y momentum equation and found that they were much smaller than this order of magnitude, right? So they're all delta L times rho u infinity squared over L. So what that tells us is that the y momentum equation is not very important in a boundary layer. None of these terms are very big, and in fact, if you want to think about it physically, what it really tells you is that the pressure gradient in the y direction is really small. This pressure gradient in the y direction is going to be of order of any of these terms that are left, and these terms are all really small. So we can approximate the pressure gradient in the y direction as being 0. And what that really means is that as you move from the surface of your object through the boundary layer to the free stream, the pressure doesn't change much, right? That pressure is pretty much constant. The pressure might change as you move in the x direction, so as you move along the surface, and how much that pressure changes, has a lot to do with what kind of surface we're talking about. But across the boundary layer, the free stream pressure basically impresses itself through the boundary layer and sort of determines what the boundary layer pressure is, right? So practically what that tells us is that as we go from these partial differential equations that are not simplified to over here we're starting to simplify them, the continuity equation didn't change, but it did give us a scaling for v delta. The x momentum equation changed a little bit in that one of these terms went away, this one went away. And then the y momentum equation, basically the y momentum equation can just go away, and we can be left with this idea that the pressure gradient in y is equal to 0. And if you come back and look at what dp dx is now, then if p is only a function of x, because it's not a function of y, then dp dx is actually the free stream pressure gradient. It's dp infinity dx. It's some pressure gradient. It's the x derivative of some pressure function that is related to how the free stream is flowing around an object. And that ends up being basically a lot about what the object itself is, right? And that impacts the boundary layer through this equation right here, but it's not an outcome of our boundary layer solution. All right, so we have one more equation to do, and that's the energy equation. So that's what I'm showing here. There's these four terms. We have advective energy transport, so these are energy terms related to mass transfer, and then we have conduction, and then this is our viscous dissipation function. This is related to the rate at which thermal energy is being generated due to viscous dissipation. So the first thing we can do is look at each of these terms right here. And we actually can do this almost by inspection, I hope, at this point, by remembering two things. We got to remember that U velocities are much bigger than V velocities, right? And we also got to remember that things change much more slowly in the X direction than they do in the Y direction. And if you keep those two things in mind, you ought to be able to know, to tell me which of these four terms is the most important and which of these four terms is the least important. And so only one of these terms is actually going to be retained in our boundary layer simplifications. And this actually is your quiz, right? Your quiz is basically to rank these in order. So the most important term in this equation is, I hope, obviously du dy, right? U tends to be pretty big, and changes in y tend to be pretty small, so this is big over small. That's going to be a big number compared to some of these other ones, right? This is small over big, small over small, and big over big, right? So you should be able to put those in order in a boundary layer, right? So the only one we're going to retain in the boundary layer is this one right here, which gives us that. If I substitute this back up into here, this is my viscous dissipation function in the boundary layer. So we still have to go look at each of these other terms and figure out if one of them can be eliminated. You know, I would hope that maybe at this point you could look at these two terms and figure out which one we're going to end up getting rid of, but let's do it formally anyway. So this is the order of magnitude of the 5 terms that we have left. Right? If I start over here on the left, I have rho c, this is going to be a u infinity, and then dt dx. So in order to get an estimate, in order to find the order of magnitude of dt dx, I do need a reference temperature change, right? And we'll call that delta T. So delta T is going to be, for our problem, a reference temperature change. Most times you would take that to be the difference between the free stream temperature and the surface temperature, right? That's the reference temperature change driving temperature differences. And then here we have dx, which we'll use L for. And we have rho CV dt dy. So here we'll have V delta, and then the same reference temperature change, and then dy is going to be delta. If I plug in V delta here, I find that this term and this term are the same. Here I have K, and then the gradient of the gradient, right? So this is the second derivative of T with respect to X. That will be delta T over L squared. This will be delta T over delta squared. And this is going to be mu times u infinity over delta, both squared, right? So these terms here have the same order of magnitude. So if I want to look at how these terms over here compare, I just take this whole equation and divide through by the order of magnitude of these terms, which is what I did here. I divided through by rho c u infinity delta t over L. Of course, when I do that, these two terms go to 1. And the real question then is, what are these two terms doing? We're going to leave this term alone for now, since it's not obvious how to scale it. We'll come back when we do our dimensionless equations, but let's take these two terms. So this first term here, pointer, this is the order of magnitude of k times d squared t dx squared, and we're dividing through by rho c u infinity delta t over L. So we already said that the order of magnitude of this first term is k delta t over L squared, and we divide through this. And if you do a little bit of algebra, you can find that it becomes 1 over the Reynolds number times the Prandtl number. And that little bit of algebra consists of canceling the delta L's, or I'm sorry, the delta T's, canceling one of these L's here, and then recognizing that k over rho c is alpha, right? So that leaves you with this. And then if you multiply and divide by kinematic viscosity, you have Reynolds number. So the Reynolds number is this, and then Prandtl number right here. So 1 over Reynolds number, Prandtl number. And again, remembering that this whole analysis is based on the idea that the Reynolds number will always be a lot bigger than 1, and that the Prandtl number isn't that different than 1. this term must be small, right? So this term here must be negligibly small relative to these terms over here. So we move on to this term, the second conduction term, and see what we get. So same idea, right? I'm going to take the order of magnitude of this term, which is k delta t over delta squared, and divide it by rho c u infinity delta t over L. Do a little bit of algebra, right? And again, it's not difficult algebra. You're just going to, in this case, multiply and divide by L, cancel out your delta t's, and you end up with, I guess, this right here. And you multiply and divide by the kinematic viscosity, and you get this term here. And again, sort of like before with the momentum equation, the first part of this term is really big, the second part of the term is really small, and if you multiply them together, you'll find that basically they cancel it, and you end up with this term having order of magnitude of 1. So this term is going to have the same order of magnitude as these guys over here. And again, that makes sense given that that's sort of what defines a laminar boundary layer. So this last term here we're going to keep, and we're then done with the boundary layer simplifications. We've actually made quite a bit of progress. If you look to the left, these are the differential equations that we derived. You know, we took a little while to get them. They were pretty complicated. And then by just sort of going through and looking term by term at these equations for the case where we're in a boundary layer, we're able to simplify them quite a lot, right? So they become these equations over here. The continuity equation didn't change. The x momentum equation got simpler, and actually also this pressure gradient term became an input to the problem in that it must be related to the free stream pressure gradient because the y momentum equation goes away. And then our energy equation got quite a bit simpler as well, right? We have over here energy transport by mass that must balance energy transport in the y direction by conduction, and then there will be some situations perhaps where this viscous dissipation will also be important. So these are simple, simpler, I guess I should say. They're not simple. They're still certainly complicated enough that they're not that easy to solve, and so as a result, the last thing we're going to want to do here is put them in dimensionless form. And we do that mostly because then we can figure out how we can get solutions for these problems and express those solutions in the minimal possible number of parameters, right? We can take a solution that might depend on 6 or 7 dimensional quantities and express it instead in terms of just a couple of dimensionless quantities, and we can get a lot of utility then out of a limited set of data or a limited set of simulations.